Okay, I think we'll get started. So today we're going to talk about this really interesting idea of the Blaschke ellipse. It's some beautiful geometric properties arise when we consider the zeros and the critical points of these Blaschke products. So first of all, if we're going to consider, throughout this, we're going to use as example the degree 3 Blaschke product. So, and also normalized. So we're going to have a 0 at 0, and then we're going to have two non-zero zeros. So these zero positions will be somewhere else. Now it turns out that there's something called the hyperbolic Gauss-Lucas theorem that says that if we draw a hyperbolic triangle, so we draw a hyperbolic geodesic for each of the sides of this triangle, the critical points are located inside that hyperbolic triangle. That hyperbolic triangle is referred to as the convex hull of these zeros, hyperbolic convex hull of these zeros. Now, it was also discovered that if you take a target point on the unit circle and look at the pre-image of that, so what are the three values in a degree 3 Blaschke polynomial that will give you that target value on the unit disk, then you can take those three values and you can create a Euclidean triangle with by each of those pairs. And every time the two non-zero zeros will be inside that Euclidean triangle. And if we take then the whole bunch of different target points around the whole unit circle, it traces out the tangents of those trace out this ellipse where the foci are at the two non-zero zeros, and that's called called a Blaschke ellipse, and it's a special type of Poncelet curve. And a Poncelet curve is one where you have a curve inscribed inside a triangle that's or a polygon, but a triangle that's inscribed inside this unit circle. Well, it's interesting as well that if you take the hyperbolic triangle, so just instead of Euclidean, but we go to hyperbolic geometry, things change a bit. We get a hyperbolic ellipse, and the foci of those ellipses are the critical points. So there's this really interesting transition from Euclidean geometry to hyperbolic geometry that's there. Now it turns out that the critical points are always inside this hyperbolic triangle, and that was proven much later. I think it was like 2006 by Singer, proved that. So what we're going to be able to show, and I haven't seen this shown, but it's obvious that since these are always inside this triangle, and these are going to be inside this ellipse, then we have a stronger confinement of where these lie. Yes, they're in the convex hull. Yes, they're in here. They're in both, so they have to be in the intersection of those. The other thing that's new, although I haven't been able to give some real mathematical proofs, but just we'll see this numerically and graphically, is we can find there's special points of there's special values of these where these are confluent, or they come together and are degenerate. And so these have some interesting properties as well. So we'll take a look at that. So we'll sit down here at the computer, and again, this will be quite different than the other lectures. We'll go through some of the notes that I have, and also run some Python programs to look at some things numerically and graphically. All right, so let's start first. I'm just going to define some zeros here. So we'll just look at these zeros, and I'll go ahead and run this. Oops, I got to change this a second. Well, okay, so what we see here, the red dots are the non-zero zeros, and then this is one particular triangle. So the target point was 1. It just so happens it's because this is a normalized Blaschke product, then one of the pre-images is 1, and then these are the other pre-images, and we form this Euclidean triangle. Let's go ahead and add a bunch more points. So I'm going to see if I can find that quickly in my code here. Whoops. Okay, so instead of one triangle, let's do 36 triangles. And that should give us a pretty good picture. And sure enough, when we now take all these different triangles and swoop them around the unit circle, we form an ellipse. You can see kind of the ellipse here, and the foci of these ellipse are the two non-zero zeros. The other zero is sitting right here at 0, 0. Okay. Now we can change this a bit. Let's change our zeros. Let's make this a 0.8. Give that a try. And notice here now, the 0, 0 is not in this ellipse anymore, but again, we have this ellipse. And as we push this out further, let's see, gotta be careful that I don't go outside the unit circle, but as we push this out further, our ellipse gets more and more distorted or elongated. Okay, so that's this Euclidean picture. Let's look at a hyperbolic picture. So now I've chosen some hyperbolic, and I'm showing a bit more here now. The red points are the zeros. So we have 0, we have these 2 points, that's going to be these 2 points. And then the red triangle, hyperbolic triangle, is the convex hull. And the pink, or the cyan squares are the critical points. And they lie within this hyperbolic ellipse, and they lie in the convex hull. So they lie in the intersection of this. Let's just try some different values here. Switch that to a minus. And again, we can see they lie in they're the center of this ellipse. It doesn't look like, it's not a Euclidean ellipse, it's a hyperbolic ellipse, but it is an ellipse. I think let's try this one. This might be a very distorted, it's right out by the edge. Quite distorted, but still behaving the way it's expected. All right, so let's look at some other cases here, and I'm going to just open up my notes. All right, so these are just some notes here, and so here's what we just saw on the Python program, both the Euclidean and the hyperbolic ellipses here. Now this is looking at the Blaschke function or Blaschke product in a little different way. These are the level sets of the real part and the imaginary part. The real part is blue and the imaginary part is red. So this is one way to visualize the Blaschke product. And these are the zeros. And then these are the critical points in magenta here. This over here is the derivative of the Blaschke product, and we can see the zeros of the derivative are the critical points over here. Okay, so now I'm going to swing down a little bit and pick up one quick theorem, which I kind of alluded to. So as we look at this, we can say for sure that the critical points lie within the convex hull and within this ellipse. And so we are able to improve the tightness of that. So it has to be in the intersection of that. Okay, so what we're looking at here is a little interesting, and I alert you right away that the scale is wrong here, it's flipped, so I'll go through that. But what I've got here is I've created this heat map where we have one of the zeros is at 0, the other 0 is at the hyperbolic tangent of 1/2, which is a unit 1 length in hyperbolic distance. And then the other is free to move throughout the whole plane, or the whole disk. So as we move that third 0 around the the whole disk, what we're looking at here is the Euclidean distance between the critical points. And again, this is opposite. So red is 0 and white is larger. So this, my scale got flipped, which I have to correct here. So this shows that when the 0 is either here or here, the Euclidean distance goes to 0, and we have a confluence of those critical points. Here's an example over here where we have one of our zeros is at 0. Here's our 0 at the hyperbolic distance, and then here's our 0 at this point right here. And we see there's a confluence of those points. They're almost together right here. And it's very numerically unstable, so it's difficult to get those right on top of each other, but you can. Now, what's one thing that's interesting is that the zeros are on this circle. This 0 is on this circle, so that's kind of an interesting aspect of this. So what I've done down here is I've looked at, see, notice here are the blacks here are 3 zeros, and then there was that symmetry. So this would be the other set. So you can look at this 0, and this 0, those are the 3, or we can look at this 0, and this 0. As we traverse this 0 along this line, this 0 goes along this arc. This is the 0 of the confluence, goes along this arc. So as long as this is along this arc, then we are going to have confluent critical points. The cyan curve here is precisely that critical point itself. So what we saw in the graph above were the choices of 0, 0, 0, and then this is where that confluence happens. Then again, there's this symmetry down here. One thing we can look at is the modulus of these two and plot them as we move this point outward. And we see that's linear, so that means they do indeed lie on a circle. So the modular distance from here to here is the same as from here to here. Then the orange curve here is the phase. So we can see this phase change because this loops up and around. We see that this phase change drops. Now, so what was interesting is that if you take these points and form a hyperbolic triangle down here, that's what's going on down here, and then you put this guy lies, the critical point lies such that these are broken up into congruent triangles. So same angle set and same perimeter and same area in a hyperbolic sense. So they're hyperbolic triangles. And this is true no matter where you go. Now, I haven't proven that, but I've sort of shown it numerically that these are congruent triangles. So although they don't look it, it's hard to see these. It's hard to make sense of these hyperbolic triangles. These are all congruent hyperbolic triangles. And so that's kind of a neat aspect of this. All right, so this was a very different type of lecture. So it just kind of showed some of the various this very interesting geometric relationship between the zeros and also between the critical points. And what I think is so neat is how a transition from Euclidean geometry to hyperbolic geometry just switches from the zeros to the critical points.